Hey guys, here are your notes on section 3.4, day 2. But before I do that, I just want to finish the last problem from the day 1 notes on the Golden Gate Bridge. All right, this problem said the Golden Gate Bridge, a suspension bridge, spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from 2 huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. Find the height of the cable above the road at a distance of 1,000 feet from the center. All right, so guys, first of all, you have a bridge that's sitting 220 feet above the water. Okay, then you have a cable that is parabolic in shape that is hanging in between 2 towers that are 4,200 feet apart. They have the road of the bridge acting as your x-axis, and then they have the y-axis coming right from the center of that bridge. All right, so the cables, they say they hit the road right at the center of that bridge. So they're calling that point where the cable hits the road point 0, 0. All right, well, the cables or the towers are 4,200 feet apart, right? So since this is the center, if you cut 4,200 in half, that means 2,100 feet to the right is a tower and 2,100 feet to the left is a tower, all right? The tower was supposed to be 746 feet tall, but the tower goes all the way down to the water, which means you're going to take off 220 feet from the 746, leaving from here, your x-axis to there, 526 feet. So that's where these 2 points come from. So you have a parabola centered at 0, 0, and you know the points 2,100, 526 are on that parabola, and negative 2,100, 526 is on that parabola, okay? They want to find the height of the cable above the road at a distance from 1,000 feet from the center. So they're saying 1,000 feet to the right of your center. They want to know what is the height of that cable right there. Okay, well, first we have to come up with an equation. Well, the equation is pretty simple in the sense that the parabola itself is centered at 0, 0. So guys, we have vertex form to write the equation of a parabola, especially when you know the center, right? So if the center is 0, 0, that's going to leave you with y equals a times x minus 0 is x, squared is x. So you basically get x and then squared and then plus 0. So really it becomes y equals a times x squared. That's going to be the equation of your parabola right now with a center at 0, 0. So we do need an a value in order to work with this equation. Well, we do know a point or a couple points that are on this parabola. I do know these 2 points on the parabola. So I'm going to use this one, 2,100, 526, and I'm going to plug it in as x and y to solve for my a value. So 526 equals a times 2,100 squared. Well, divide by 2,100 squared, and you find out that a is equal to 526 divided by 2,100 squared, which is a pretty big number. So I'm going to leave it as that, 2,100 squared. So now the problem the equation becomes y equals 526 divided by 2,100 squared times x squared. So now if they want to know what is that, and the way it's going to work is the x goes in as the distance from the center of that road, and then the height of that cable will come out. So if they want to know what is the height of the cable, 1,000 feet to the right of my center, x is 1,000, and then the height of that cable right there will be my y. So all we have to do is plug in 1,000. So y will equal 526 divided by 2,100 squared times 1,000 squared, and y will equal, let's ask our calculator to do this. Okay, let's see. 526 divided by 2,100 squared, and then we are what? Timesing it by 1,000 squared. Hit enter, and it's about 119.27 feet, I believe we are being measured in, from the center of that road, or the bridge, I should say. So y equals 119.27 feet from the center of the bridge. Oh, actually, I apologize, guys. That's the height of the cable when it is 1,000 feet from the center of the bridge. Okay? All right, so Let's go to the other day's notes. Sorry, I'm distracted. I'm just trying to find the right paper. Okay. So here we go. So then here are your day 2 notes then. All right, this one says, a rain gutter is to be made out of aluminum sheets that are 12 inches wide by turning up the edges 90 degrees. What depth will provide a maximum cross-sectional area and hence allow the most water to flow? So guys, if you picture this, I have a different picture I'm going to use. If you picture this, you had a sheet that was 12 inches, right? You're going to basically cut in X inches and X inches, and you're going to make these folds. And now turn these up on their side to allow water to flow through. So you're taking a 2-dimensional sheet and you're turning it into a 3-dimensional sheet, which now becomes a cross section. So if the entire sheet was 12 inches, once you take off X and X this way, it leaves this to be 12 minus 2x inches wide. So now you have 12 minus 2x, and then it's x and x that folds up. Okay, so they want to know what depth will provide maximum cross-sectional area. Well, guys, the area of this sheet, the area used to be good old length times width. But now the way it works, now it's like length times height is your cross-sectional area. Okay, so we have to be all in terms of one variable. I can now rewrite the length and the height in terms of x. So now the area of this cross section will be equal to 12 minus 2x times x, which if I clean that up, area will equal, I'm just going to backwards distribute here and rearrange, negative 2x squared plus 12x. All right, so now we have an equation that will find the area of this cross section. Since it's got a negative leading coefficient to this quadratic equation, we know it's represented by a parabola that opens down. So the way this works is x goes in as the depth of that cut, and then the area of that cross section will come out. So if they want to know what depth will provide maximum cross-sectional area, they need the x coordinate of the vertex. So a little negative b over 2a will get us this answer. So x equals the opposite of b over 2 times a. So negative 12 over 2 times negative 2 is negative 12 divided by negative 4, and we get 3. So with a depth of 3, I believe we're in inches, with a depth of 3 inches, that'll get you your maximum cross-sectional area, okay? So that was part A. Part B. Part B asks, well, what depths will allow at least 16 square inches of water to flow? So basically, if this is your parabola, they want at least 16 square inches to be the maximum area flowing through, right? So there's an x value here and there's an x value here that will make 16 inches of water flow. And then any x value in between will make a greater area than 16. So we want to find out what makes it at least equal 16, and then any x value in between will also qualify as an answer. All right, so what's going to make this equation negative 2x squared plus 12x equal a maximum of 16, right? Or at least an area of 16. All right, so let's just add everything over. All right, I'm going to minus the 12x plus 16 equals 0. I'm going to factor out a 2. Okay, and then I'm going to factor it. Looks like it's going to factor quite nicely. X. What adds to negative 6 and then multiplies to 8? Minus 4 minus 2. Little zero product property, set your factors equal to 0, and you find out that when x is 4, a depth of 4, and when x is 2, they create a cross-sectional area that is 16, inches squared, square inches of water flow. So then anything in between an x value of 2 and 4 will make a cross-sectional area greater than 16. So we need our x to be in between 2 and 4, including 2 and 4. So as an interval, x could be a number in between 2 and 4. And then as an inequality, it would look like that to be a number in between 2 and 4. Okay? All right, perfect. All right, one more problem. And then that'll be good for the day 2 notes. I think I drew a picture to go along with this one. I don't know where I put it. Here it is. Okay, so this one says, a track field playing area is in the shape of a rectangle with semicircles at each end, right? So we have a rectangle, and then we have a semicircle and a semicircle to make up this track and field playing area. The inside perimeter of the track, so the inside perimeter all the way around, is 1,500 meters. What should the dimensions of the rectangle be so that the area of the rectangle is a maximum? Okay, let's get ourselves organized, okay? First of all, number one, their goal is for the area of this rectangle on the inside of this track to have a maximum area. So we want the rectangle with a max area. Okay, well, first of all, how would you even find the area of a rectangle? The area of a rectangle would be equal to the length times the width, right? All right, we want to maximize that. Well, first of all, we have to get the area of this rectangle all in terms of L or all in terms of W. We need all of the area to be expressed as one variable. Then we can maximize it. So we're going to need to develop a relationship between the length and the width of this rectangle. All right, well, what did they tell us? What can we go off of? So the second thing we need to do is we need to make a relationship between L and W. So we can get L out and W in, or vice versa. We'll do whichever one is easier. Okay, let's see what we're playing with. They told us that basically the only thing they told us to go off of is that the perimeter of the inside of this track all the way around is 1,500 meters. So you got to think about, well, how would they have found the perimeter of this inside of the track? Well, perimeter just means you're adding up all the sides, right? So what would you have been adding up to find the perimeter of this track? Well, I think we'd all agree you'd have to be adding up a length and a length, right? And then you'd be adding up half of a semicircle, half of a circle, and then half of another circle. And then that would qualify as the perimeter, right? A length plus half a circle plus a length plus half a circle. So the perimeter is equal to L plus L, which is 2L, plus, do you guys agree that half the distance around a circle there, that's kind of half of the circumference, and then this is half of the circumference, the distance around a circle. So when you put this half of a circle together and this half of a circle together, it's one full circle, so it's one full circumference. And I'll just say circumference, okay? Well, how do you find the circumference of a circle? It's 2 pi r. So the perimeter equals 2L plus 2 pi r. But guys, we can make this even easier. Because the width of our rectangle is also the diameter of that circle, we can do 2 times r is d. 2 times the radius is the diameter. And since the diameter is my width, I think that would be easier to work with. So the perimeter is equal to 2L plus, instead of 2 times r, we're going to do pi times diameter, okay? All right, now we're getting there. Well, since I just said that the diameter of this circle is equal to the width of that rectangle, now we can take the diameter out and put the W in, right? We're trying to build a relationship between L and W. So I don't really need another variable in there, diameter. So now the perimeter is equal to 2L plus pi times W, right? And there's one other thing we know. They told us that that perimeter is 1,500. So I know I can put 1,500 in for P, and now I'm only working with an equation that has an L and a W in it. So now, in order to get L and W, or L or W out of this, I can solve this for L, or I can solve this for W, and then I'll be able to get one of these variables out, and this area will be written in terms of just one variable. So if you think about it, if I want to solve for W, I'm going to minus my 2L over, and then I'm going to have to divide everything by pi. Ooh, that's going to be a little ugly. But if I choose to solve for L, then I'm just going to have to minus the pi W over and divide everything by 2. So that sounds a little bit nicer. So I'm going to choose to solve this for L because it looks like it's going to be the easier choice. So if we solve this for L, right, we're going to get 1,500 minus pi W comes over equals 2 times L. Divide everything by 2. And you end up with the length of the rectangle is equal to 1,500 divided by 2 is 750. And then I'm just going to take pi and divide it by 2 and then times it by W. Okay, so there is the length of your rectangle. Now we can take the length of the rectangle and plug it in for L, and then I'll have an equation that's all in terms of W. Okay, all right, so area equals, not length anymore, 750 minus pi over 2 times W, and then times W again, right? Times that W. All right, let's distribute. And we're going to get the area of the rectangle is equal to 750 W minus pi over 2 W squared. Again, I have a little OCD, so I like to rewrite that as negative pi over 2 W squared plus 750 W. Okay. All right. So now, if you want to find the dimensions of the rectangle that maximize the area of that rectangle, well, W will go in and the area of that rectangle will come out. So we want to find the length of that width. We want to find that W, so we want the x coordinate of this vertex, right? The equation we just wrote will be modeled by a parabola that opens down. So the highest point will be his vertex, and the W will be his x. The width will be his x, and the area will be his y. So we need the x coordinate of this vertex. So just a little bit of negative b over 2a. All right, so W will equal the opposite of B over 2 times A. So the opposite of B is going to be what? Negative 750 over 2 times A is negative pi over 2. All right, they're actually going to cancel the 2's, and then a negative over a negative is positive. So your width is going to be equal to 750 divided by pi. And I'm going to leave it exact like that until we move on in the problem. So the width that maximizes the area is 750 over pi. So now to find the length, we're trying to find the dimensions of this rectangle that maximize the area. I know the width that maximizes the area. Now I got to find the length. So now you're going to plug what you just found out the W is, 750 over pi, in here, and then we'll find out what the dimension for the length is. All right, so the length will equal 750 minus pi over 2 times W, which we just found out was 750 over pi. All right, so the pi's end up canceling, and the length will be equal to 750 minus half of 750 is going to be 375. So then 750 minus 375, it leaves the length of the rectangle to be 375. All right, perfect. And what are we working in? We're working in meters, it looks like. Okay. All right, so now there's the length that maximizes the area, and the width was 750 divided by pi, technically meters. Now they might ask you for rounding this to the decimal. So now if I ask my calculator, what's 750 divided by pi? It's 238.73. Meters. So again, I can't remember. They may ask you to round that answer. And then I think they just have you list them on the homework with a comma. They just have you list them. Doesn't matter which one's first, with a comma in between. Okay? All right, guys, that's it for today's notes. As always, please always reach out to me if you have any questions.